Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on carboxylic acids and derivatives. Now this video is dedicated to AQA, so none of this information here is generic information. It is actually designed around the specification for AQA. So if you are studying A-level chemistry for this exam board, then this is perfect for you because it contains all the information you need to know and nothing more. Also, there's a full range of these types of videos, these are revision videos, on Allery Chemistry YouTube channel. So if you just go and have a look, there's a full range from year 1 all the way through to year 2. So it's quite a comprehensive range. There's also some whiteboard tutorials as well on the channel, which will go through specific parts of chemistry. So it's not specific to any part of exam board. So it's just there for your information if you want to look at a specific type. And also there's information on there about exam technique. So we're going to do some exam past paper walkthroughs. All of that is for free, so all I ask is you hit the subscribe button to show your support and to get any updates. That'll be absolutely fantastic. That'll be brilliant. Also, these slides here, my mind went a little bit blank there. These slides here are also available to purchase if you would like a copy of them. So if you click on the link in the description box, you can get a hold of them there. But they are great value for money because you can use them on the move, your tablet, smartphone, and scroll through them at your leisure. Also, I know people who've got them and they print them off and they use it as part of their revision notes. They annotate them, etc. So click on the link. The full range is there for year 1 and 2. Everything is there. Okay, so like I say, this is dedicated to AQA and it meets these specification points. So it's split up into two main types. The first type being carboxylic acids and esters. So it's going to start by looking at carboxylic acids and esters. And then we're going to be looking at acylation reactions as well. So looking at acyl chlorides, then looking at things like biodiesel and fats and vegetable oils, and then finally looking at some practical techniques. So that's the kind of running order for this video. Okay, so we're going to start by looking at carboxylic acids. So carboxylic acids have this carboxyl group. That's a COOH group. Okay, very important. It contains both the carbonyl group, which is the C double bond O, and the hydroxyl group OH. Now, you might have seen carboxylic acids in year 1. You might have seen bits of them there. This topic is really going to go into a lot of detail about carboxylic acids and look at esters and all the derivatives. Derivatives, obviously, just anything that's spawned from carboxylic acids. Excuse me. So they are named by finding the longest carbon chain, just like you would do with any other group, such as a aldehyde or a ketone or an alcohol or anything like that. We find the longest carbon chain and we end it with oic acid on the end. Okay. So when we're naming carboxylic acids, the carboxyl group is always carbon 1, so that makes it nice and easy, nice and straightforward. And the carboxyl group must also be at the end of the molecule. You can't have a carboxyl group midway through the molecule, so it's always at the end. It's always a terminus functional group. So let's have a look at an example here. So we've got ethanoic acid as the first one. See, it's got 2 carbons there, and your carboxyl group is obviously at the end. There it is. There's your carboxyl group. Okay, and obviously this is ethanoic because you've got 2 carbons, so it's eth for 2. Just to complicate it a little bit more, we've got this one. Now, this is just to kind of show you how this carbon 1 works. Remember, it's always carbon 1. So you can see here, this is carbon 1, that's 2, and that's 3. So on carbon 3, you've got hydroxy on there, and in carbon 4, you've got chloro. So it's always numbered from carbon 1, and your carboxylic acid's always at the end. So this one's 4-chloro, 3-hydroxybutanoic acid. And you can also get aromatic ones as well. So this is benzoic acid. So you can see you've got a benzene there with a carboxylic acid group or carboxyl group right at the end there. So you can see there's a variety of different types of carboxylic acids. You've got obviously the ones with some groups coming off it on the main carbon chain. You've got straightforward ones and you've got aromatic ones. So just as long as you're aware of the naming of it and the carboxyl group is always carbon 1, that's the main thing. Okay. So carboxylic acids are actually weak acids. As the name suggests, they're acids, obviously. So they're weak acids, and they react with carbonates to form carbon dioxide. So they behave in exactly the same way as other acids would. So acid plus base gives salt plus water. Acid plus carbonate gives salt plus water plus carbon dioxide. There's no difference here between any other acid. So there's nothing significantly new. So they are weak, so it means they dissociate quite poorly. Now, if you remember from the acid-base topic, I don't know if you've gone through that, then that's fine. I've done a video on that if you haven't, looking at acid-base topic. But you'll know that with weak acids, they dissociate weakly. Okay, so in other words, they don't dissociate. They don't dissociate fully, so they don't produce many H plus ions. Equilibrium lies well over to the left, as you can see in this diagram here. So you've got your carboxylic acid in equilibrium with the carboxylate ion and the H plus ion. So equilibrium lies well over to the left. We've got loads of the carboxylic acid, and we haven't got much of these at all. Okay, so it's equilibrium lies to the left, so it dissociates poorly, as we said. So as the acids, like I say, they react with carbonates like any other acid would, and they'll form salt, carbon dioxide, gas, and water. So let's have a look at an example. So this is a one with ethanoic acid reacting with sodium carbonate. So you've got your ethanoic acid, which is here. There's your ethanoic acid, sodium carbonate, and obviously we're forming sodium ethanoate. That's our salt, plus water, plus carbon dioxide on the right there. Okay. So we've also got another reaction. This is with sodium hydrogen carbonate. Same type of reaction, still acid and base, and that will form your salt plus water plus carbon dioxide. It's just we're using a hydrogen carbonate instead of just a carbonate. Okay, so that's the kind of the basics, the basic introduction to carboxylic acid. So now what we're going to look at is what we can do with carboxylic acid. So what reactions are they involved in, and some of their derivatives from that. Okay. So first of all, we're going to be looking at the formation of esters, okay, or what we call esterification. So that's one reaction that you really do need to know, where we're reacting the carboxylic acids with an alcohol, okay. So we can react them with, reacting alcohols with carboxylic acids and acid anhydrides, as you're going to see later on what they are. These can be used to make esters, because esters have the COO group on them, okay. You might have seen esters already. You might have even seen them at GCSE, possibly, depending on the spec that you've done. But effectively, they're made by reacting alcohol with a carboxylic acid, or it could be an anhydride as well, acid anhydride. So an ester, like I say, is produced when we react a carboxylic acid with an alcohol, and we use a sulfuric acid catalyst. Okay, now if you've seen the transition metal topic, you would see that sulfuric acid is a homogeneous catalyst, so it's integrated within the actual reaction. So it's always reformed though, because that's a catalyst. So an ester is also produced, like I say, when reacting acid anhydride reacts with an alcohol, but we'll look at this later on, because acid anhydride really falls into the derivative section, which we'll look at towards the middle to the end part of the video. So let's have a look at a reaction here. So you can see we've got a carboxylic acid, and it's reacting with alcohol, and we've colour-coded it so you can see what's going where. So carboxylic acid atoms are in blue and your alcohols are in yellow. So you can see here that we've got our carboxylic acid bit here and our alcohol bit here. So the hydrogen here and the OH basically drop off and they form your water molecule here. So it's just showing you how it's all structured. It is in equilibrium, and we do have an acid catalyst. Obviously that's our sulfuric acid catalyst that we're using there. Okay. Same reaction happens with anhydrides as well. So anhydrides, just to give you a brief introduction to what they are, because you do need to know about them eventually. But anhydrides are basically like carboxylic acids, except instead of a H here, it's bonded directly to a carbonyl group, so a C double bond O. So it looks like a carboxylic acid that's like cut in half. And there's a bit of symmetry with these as well. So the only ones that you need to know for acid anhydrides are the symmetrical ones. In other words, the ones with the same number of carbons on the top as they are on the bottom. Okay, so they're the ones which you'll be expect to name them. You might see ones that might be asymmetric, but the reaction's exactly the same. But you're only expected to name the ones which are symmetrical. Okay, so you got your alcohol, as expected, and that will form your ester, but instead of forming water, we form carboxylic acid. And again, it's all been color-coded so you can see what's going where. Okay, so esters, they are actually named in two ways. Okay, well, not two ways, one way, but they're in two sections. Okay, so the first bit is named from the alcohol that was used, and the second bit is named from the carboxylic acid. So let's have a look at an example where we're reacting ethanol with propanoic acid. Okay, so you can see this is the ester that we form here, but we need to be able to name it. So remember, we've got to name it. We'll kind of almost name it back to front. Okay, so we name the alcohol bit first and then the carboxylic acid. So the first bit, this bit here, So this part of the ester is formed from the alcohol and is the alkyl group. So this is ethyl because it's got 2 carbons and is named first when we're naming an ester. And obviously the second bit is this bit here. This is named from the carboxylic acid, and all we do is remove the oic acid bit from the molecule, from whatever we've got, and replace it with OAte. So in this example it's propanoate. Okay, and this is always named second when we name an ester. So it's always the alcohol bit in red, then the carboxylic acid part in blue. So the full name of this is ethyl propanoate. Okay, so ethyl being the red bit, propanoate being the carboxylic acid bit. So it's all been color coded so you can see what's going on. Okay, let's have a look at another example of naming an ester. We're going to make this a little bit more complicated. Yep, we've put a methyl group in there. So this is reacting ethanol with 2-methyl propanoic acid. Okay, so when we name an esters, okay, what we have to do is with an alkyl branch is we number them from the COC part. So that's this bit here. Okay, so we always number it from here. So that's carbon 1, 2, 3, and that's carbon 1, 2. So we never name it the other way. So we always name it closest to this group here. That's the first thing we should say. So this part of the ester is formed from the alcohol. Okay, so just as normal. So this is your ethyl group. And then this bit is formed from your carboxylic acid. So this is 2-methyl propanoate. So this, the methyl group, as you can see, sits on the second carbon. So therefore it's called 2-methyl propanoate. So the full name is simply ethyl 2-methyl propanoate. Okay, so you can see how straightforward it is. It's obviously logical and structured. I know you have to name it back to front in this case, but as long as you know the rules, you should be able to name any ester that you have in front of you. Okay, so esters are used commercially in industrial processes. Okay, so esters are actually really useful. They're all over the place in terms of foods and perfumes and other reagents like that. Normally they're classed as E numbers. So let's have a look at the first example. So it's perfumes and food flavorants. So some esters have a sweet smell. So if you've ever made esters at school or college, then you'll know that they have a distinct smell. Some of them smell really, really horrible. Some smell like rancid sick or rancid butter. Some of them smell nice like pear drops. So that's a classic sign of an ester. Obviously, it depends on what alcohol and what carboxylic acid you're reacting it with. So this makes them ideal to be used in the perfume industry, the fragrances, and the food industry as well. So like I say, in food industry, they are classed as E numbers. Okay, so they're also used in solvents as well. So esters are polar, and so other polar compounds will dissolve readily in esters, such as water, for example. They have low boiling points, they evaporate easily. That's ideal for glues, for example. So if you put glue on a surface, you want it to be liquid, and then over time you want the solvent to evaporate, and that leaves behind a hardened resin that effectively sticks something together. So it's like a solid product that's left behind. So they are used a lot in glues, and they're also used in plasticizers as well. So this is where you want to make plastics more flexible during that polymerization period. So for example, you can see the rubber ducks in the background, so they're quite soft and squidgy, so you can squish them. And that's because they have plasticizers in them. You've got to be careful though with plasticizers, and there is obviously strict laws regarding this, regarding the use of plasticizers in plastics, particularly in children's toys, because children put, especially younger children, they'll put things in their mouths, and if they've got a plasticizer in there that leaches out readily and is toxic, then that isn't great. So the strict standards that are set when developing products, particularly when there's plasticizers involved. But naturally, over time, plastics do become brittle. They don't last. Some do last a long time. Obviously, the degradation of plastics is quite slow, and sometimes they really don't decompose that well. But if you leave plastic out for a long period of time in the sun, and it's allowed to break down using UV light coming from the sun, then eventually the plastic will become brittle. You might see this outdoors. If you look at some of maybe plastic garden furniture or anything that's plastic outside, you'll see the effects this can have, particularly if it contains a plasticizer. Okay, so we're going to look at ester hydrolysis now. Okay, so we've looked at how you make an ester. So you make an ester by using a carboxylic acid or acid anhydride, and you react that with an alcohol. So this is where, okay, we've made the ester, but we want to break it down. We want to break it into the molecules that we use to make it in the first place. And we call this hydrolysis. Now, hydrolysis just means split with water. So hydro meaning obviously water, lysis meaning to break. So hydrolysis means to break using water. However, it can be sped up using an acid, so we call it acid hydrolysis, or a base, and we call that base hydrolysis. So it's fairly straightforward. We're going to look at acid hydrolysis first. So here we're going to use a dilute acid to split an ester into a carboxylic acid and an alcohol, okay? So basically it's just splitting this, remember it's splitting these two apart. So we can use sulfuric acid or hydrochloric acid, and all of this is conducted under reflux, and you'll see this towards the end of the video when we look at practical techniques. Reflux is used when we're heating volatile liquids. We want the benefit of the heat to allow them to work, but we don't want our products or reactants in that case to just evaporate off into the atmosphere. So reflux allows us to do that. So here's the first one. This is your ester. And you can see here this ester is ethyl ethanoate, and we're going to obviously react it with water because it's hydrolysis, but we're going to have an acid catalyst in there, hence the H+. Now this is going to form two products. As you've seen them already, you know we form a carboxylic acid and alcohol, but just to show you where it all comes from, remember the red bit comes from the carboxylic acid. Now the OH to finish off the carboxylic acid comes from the water, and then you've got your alcohol as well, which is the blue bit, and again the final hydrogen comes from the water molecule. So we're just using acid here to help kind of catalyze this reaction, okay, to speed it up. Okay, so still looking at ester hydrolysis. We're going to look at base hydrolysis now. So base hydrolysis is basically where we use a base to split an ester. It's exactly the same as what we've seen before, so it's no different except we're using a base. The products are marginally different because you form an ion, but you form a carboxylate ion and an alcohol. So we use the base that we use is sodium hydroxide. Again, it's all conducted under reflux, as I've mentioned before, for the same reasons. So let's have a look. Here's our ester, and this time, as you can see, we're reacting it with our OH-. We're using an OH- ion here, so it's our base hydrolysis. And we form our carboxylate ion, and we also form alcohol as well, okay? So just remember, hydrolysis is hydrolysis, if you had to break it down or split it up. So you can say hydro, meaning water, lysis just means to break. So hydrolysis means to break using water, but sometimes we can use a bit of help from an acid and a base. Okay, straightforward, pretty much. Okay, it's just the reverse of esterification. Okay, so we're going to start and look at, obviously that's the first derivative that we looked at, and that's an ester. Well, it's kind of a derivative. It's actually, it's not a derivative, is it? So it's actually made from carboxylic acids. But this here is a derivative, and we're going to look at fats and oils. So I quite like this bit because it actually links together something which may look quite detached from everyday life. We're going to bring these esters and carboxylic acids together, and we're going to actually look and see, how do these esterification reactions translate themselves into everyday life. And this is a classic example where I look at fats and oils. So when we react glycerol, which is just a type of alcohol, and fatty acid, which is a type of carboxylic acid, we produce an ester which makes fats and oils. Okay, so this is pretty cool. And actually there's a really good one later on where we look at how you make soap. You might have done that in the lab, in school or college, but it's a really good. I like that practical. It's probably one of my favourite ones, I think. That and transition metals is my favourite one. If you've seen any other videos, you see I'm a big fan of transition metals. Nice and colourful. Okay, so let's look at glycerol. So glycerol is propane 1,2,3 triol. Okay, so it's an alcohol, but it's got 3 OH groups. It's a triol. It's reacted with long chain fatty acids, which can be saturated, i.e. they've got no double bonds at all, or they can be unsaturated, and that means they've got at least one double bond in them, so you can get different types. So glycerol, let's have a look at the formula for glycerol. So glycerol, as you can see, is propane 1,2,3 triol. So propane because you've got 3 carbons there, and it's 1,2,3 triol because you've got 2 alcohols there. Okay, so it is just a big alcohol. That's all it is. But when you look at that, don't think, oh, that looks really different. It has an OH group on it. It's just an alcohol. Okay, so we're just using the same methods that you've seen before. We're just going to apply this. Okay, so a saturated fatty acid looks like that. It's massive. Okay, so these have obviously the carboxylic acid group, the carboxyl group at the end, but attached to this is you've got loads of carbons, a big long carbon chain attached to the side, and we call this a saturated fatty acid because it contains no double bonds. But if it did contain at least one double bond, then this would be an unsaturated fatty acid. Okay, so you can see that unsaturated fatty acids have more than one double bond, or they can have more than one double bond. These are called polyunsaturated fatty acids. Now, you might have heard some of these terms before, like saturated fats and unsaturated fats. So you might have seen these in food. So your saturated fats are the worst types of fats. So these are the ones which can increase the level of bad cholesterol in your blood and can lead to heart conditions and stroke. So your saturated fatty acids are normally found in deep fried food, greasy food like that. So say like cheese, for example, butter, lard, things like that. Particularly lard in particular, that is just animal fat. So saturated fatty acids, they're not good for you at all. Whereas if obviously you need fats in your diet, it's an important part of your diet, but the fats that you should be having are things like unsaturated fats. So these have some double bonds in there, and these unsaturated fats, they are normally found in things like nuts, for example. So nuts are rich in things like unsaturated oils or essential fatty acids as they call them. So these are the good types of fats which you need in your diet. So these are the ones that you do need in your diet. Your saturated ones aren't. So now you know the difference. The reason why it's called saturated is because if you've got a double bond in there, you have less hydrogen. So the word saturated is referring to the amount of hydrogens in the molecule per carbon. So you can see if you've got loads of double bonds in there, you haven't got as many hydrogens, so it's unsaturated. So that's where the word comes from. So if you didn't know that, you've learned something. Right, so let's have a look at how we actually, what we do when we react these together. So when we react the glycerols we've seen there and the fatty acids in the previous slides, so we've seen them already, we produce an ester, and that makes fats and oils. Okay, so these are the key things. Okay, so there we are. Okay, so an oil is an ester, and an example is shown below, and we can see the ester links. So you can see here, this is a type of oil. Okay, so we've got this has come from our alcohol. Okay, so this is our glycerol, and our carboxylic acid is here. But when we join them together, just like with any other reaction, we form an ester. Except because we've got 3 sites where these can form, we can form 3 different esters. Okay, and you can see on there. So this is an example of an oil ester. Okay, so vegetable oils, they have unsaturated hydrocarbon chains, so that are not straight, which means they can't pack together closely, and hence have lower van der Waals forces, and they have lower melting points and are liquids at room temperature. So you can see here, if you notice here, you've got some of these chains here where this double bond here is actually in a now this is a trans setup because you've got it down here and then it goes down. Okay, whereas this one is a cis setup. So you can see here, there's your double bond, and it's on the same side. So you can see it like almost forms this bowl shape here. And this one is a trans setup again. So all these chains can be in cis trans all the way through. And because of this, they really can't pack closely together because the kind of some of the chains are buckled and they can't form. You see, there's a bigger space there than there is here. So they can't pack tightly together. So that means they're not really. They've got low forces between them. So that means they're more likely to be a liquid at room temperature, and they have lower melting points as well, and boiling points for that matter. Okay, so oils are set up like that. Now, a fat is an ester. And an example's shown below, and we'll have a look here. But notice the ester links again in the blue box. It's still an ester, but notice the difference between this, which is a fat, and an oil, like a vegetable oil. So this is a fat ester. I bet you'd never think you'd describe an esters as fat esters, but yes, this is an ester that's described as a fat. So animal fats are a classic example of this, and I mentioned lard as well before. But they have saturated hydrocarbon chains. They're straight and uniform. Okay, you can see there, we don't get any cis trans because we haven't got any double bonds, so we can't have cis trans or EZ isomerism, should I say, in these molecules. So they packed tightly together. They're all uniform. They're all in line. There's no difference in the spacing here. And so therefore they have much more stronger van der Waals forces between these chains, and so therefore their melting and boiling points are higher. And so that means actually these types of esters are solid at room temperature. And you can see here that lard is just the fat. That's all lard is. It's this white bit here. And obviously lard can be used for cooking and baking, etc. So it's a type of fat, but it's solid at room temperature because of this close packing of the chains and higher van der Waals forces. So you are expected to differentiate. They might give you a massive molecule like this. Don't be frightened by it. All you're looking for is, does it have double bonds in? It's likely to be an oil. Okay, if it has no double bonds in, it's going to be a fat, and you just need to explain why. But this is just using chemistry from year one when we're looking at van der Waals forces and intermolecular bonds. Okay. So, we're going to go from oils and fats and moving away from food, and we're going to look at this one. This is what I was saying before, where we're going to look at making soap. Okay, now you might have made this in the lab at school or college, and obviously if you have access to a lab, you might have done this. It's a great reaction, and it works. It works really well. Quite often in chemistry, reactions don't really work too well, but this one really does. And so, animal fats and vegetable oils, they can be hydrolyzed. Remember, we looked at this already. There's nothing new here. We're just applying it to fats and oils instead. But they can be hydrolyzed. Remember, that's breaking it up using water. Okay, and we're heating them with sodium hydroxide, and what we produce is soap. Okay, so the example below uses an animal fat to make soap with this one, but you can use oils as well. But we're going to use an animal fat to do this. So it's a saturated ester. You can see we've got no double bonds in here. This is just an alkane chain that's attached to it, so it's definitely a fat. And then what we're going to do is react that with sodium hydroxide. Okay, so there we are. So three amounts of sodium hydroxide. And what I've done is I've color coded these so you can see where the atoms are going, because I think it's a bit complicated when you've got a lot of carbons here. So we're going to form glycerol. So there's our alcohol that's back. Okay, that's fine because it's hydrolysis. But the key thing is we actually form a salt of the carboxylic acid. So we form effectively it's a sodium salt. And that sodium salt is soap. And we know it's a soap because actually we see it's definitely a solid because you've got a big long hydrocarbon chain. But also when you think about it, when you wash your hands, you want the soap to disintegrate in your hands and get onto your hands so you can wash off any dirt that you got on your hands. So you can see here, this is definitely a salt, and this will break up when it comes into contact with water, but the integrity of the soap will remain. Most of it will remain because we've got this big long hydrocarbon chain, so there are bonds that's holding it together. So the whole thing doesn't disintegrate, at once, because otherwise you'd have a bar of soap and you only be able to use it once, and that wouldn't be very good. Okay, so that's how you make soap. Dead easy reaction, really. I mean, you can do it at home. Essentially, if you get the stuff, but you've got to be really careful with sodium hydroxide because it's concentrated sodium hydroxide. So, it's really caustic, and you really do, you can't really, handle that. You've got to handle that basically carefully, because if it gets in your eyes, it can damage your eyes, it can damage your skin, etc. So, it's probably best, obviously doing this in a lab, and with all the right equipment and protective equipment as well. But when I say you could probably do it at home, it's just because it's a simple reaction. It's pretty straightforward. You can get access to things like, fats and oils quite readily. Okay, so we're going to look at another use for this, which is biodiesel. Okay, so biodiesel is a type of fuel, and it's made from vegetable oils, and it basically vegetable oils that can be converted into this biodiesel by reacting the oils with methanol and potassium hydroxide. As a catalyst, so a catalyst basically. So this is used to power cars, and actually there are some companies that will take away old chip pan, from fryers, so deep fat fryers. So in chip shops, for example, they'll take away the old oil and they'll actually convert it into biodiesel, so they'll get some use out of it instead of just being thrown away. So biodiesel is just a mixture of fatty acids made from methyl esters, and it can be made from rapeseed oil. Like I say, rapeseed oil is the oil that's normally used in cooking oil. So here's our oil here. So what I've done is I've just shortened it a bit. The R group obviously represents your hydrocarbon chain that's on the end here. Okay. We're then going to react that with some methanol. We've got 3 molecules of methanol, and we're going to use potassium hydroxide as our catalyst. And then we form glycerol. There's our glycerol there. And obviously we're going to form methyl ester. This is our ester here. Now that ester is actually our biodiesel, and that's what we're going to then use to obviously to power a car with. So you can see all we're doing is reacting our ester with alcohol, and we form our oil, which is an ester, and we're going to react it with our alcohol, and we're going to form a methyl ester, which is what we use to power things. So you need to be able to write that down, recall that in an exam, and you need to know how we make biodiesel and what it's used for. Okay. Right, so that's the end of that bit. So now we're going to look at another derivative, and this derivative is going to be acid chlorides or acyl chlorides. So these are quite fun. Now you might have seen these again in science in your lessons. You might have seen these in school or in college. Likely these probably would have been done by a teacher or lecturer, because they are quite reactive reactions. So acyl chlorides, also known as acid chlorides, they have the functional group COCl, which contains the acyl group, which is COCl. Okay. Now acyl chlorides are named by finding the longest carbon chain and then adding oil chloride at the end. Now you'll notice this is pretty much the same as a carboxylic acid, okay? So we're naming it in the same way. We find the longest carbon chain, and except instead of adding oic acid, we add oil chloride on the end. So when naming acyl chlorides, the carbon on the acyl group is always carbon 1. Again, it's exactly the same as carboxylic acids. And the acyl group will always be at the end of the molecule as well, okay? You're never going to find it in the middle of the molecule. So let's have a look at an example. So here we've got ethanoyl chloride. So we've got 2 carbons on this. Exactly the same. 2 carbons, except you'll notice the main difference here, the reason why it's a derivative of a carboxylic acid, is because a carboxylic acid would have an OH group here, but with an acyl chloride or an acid chloride, you have a chlorine atom at the end here instead. So very similar. Let's look at a more complicated example. So this one, you can see we're still numbering from the same place. So this is carbon 1. So in carbon 2, we've got a methyl group. So that's fine. That's what we put there. Carbon 3, we've got a hydroxyl group. And carbon 4, we've got a hydroxyl group. So this is going to be 3,4-dihydroxy 2-methyl chloride. Okay, so that's how you would name that. Okay, or butanoyl chloride, sorry. Methyl butanoyl chloride. There we go. Okay, so because we've got 4 carbons there, so it's definitely going to be butanoyl chloride. Okay, so we need to look at, so now we know what acyl chlorides are, and we know kind of how to name them as well. What we need to know now is their reactions. And now there is quite a few reactions with acyl chlorides. There's 4 in particular that you need to know. And that is that acyl chlorides reacting with water, reacting with ammonia, reacting with alcohol, and primary amines. So in each reaction, basically the generic view on it is that the chlorine is substituted for either an oxygen or nitrogen, obviously depending on what you're reacting it with. So let's look at all of these 4. We need to know all 4 reactions, and we need to know what we're producing with each, okay? So we're going to start by looking at carboxylic acids first. So carboxylic acids, we have our acid chloride, as you can see there, and we're going to react that with water. And when we react ethanoyl chloride with water, we produce a carboxylic acid. In this case, it's going to be ethanoic acid plus HCl. Now you'll notice HCl is a hydrogen chloride gas. Okay, it's a really toxic gas. It's really acidic. You really should be doing this type of reaction in a fume cupboard. You shouldn't be doing this out in the open air, because you breathe that in, it's really going to irritate the lining of your lungs. And also, the reaction here is incredibly reactive. The reason why it's reactive is we've got this strong delta positive carbon here, that the water can attack this delta positive carbon, the lone pair of electrons on the oxygen can attack that, and that obviously substitutes or takes off, removes the chlorine from there, and obviously you have your alcohol, carboxylic acid group here. So this is an incredibly vigorous reaction. You really got to be very careful. This very exothermic, produce a lot of heat, and obviously you get this white misty fumes as well. Okay, let's have a look at the same thing, except we're going to react with ammonia instead. So reaction with ammonia produces amides. So here's our acid chloride, ethanoyl chloride. So we've got the 2 carbons there. And this time we're going to react it with ammonia. And so the same reaction again, very vigorous reaction, except we produce an amide. So an amide is where you've got a carbonyl group here and an NH2 next to it. So that's an amide. Don't confuse that with an amine. An amine doesn't have this group here. Okay, you've just got an amine there. And then obviously, again, we produce white misty fumes, highly acidic. Got to do it in a fume cupboard. Okay, and you can see also I've color-coded these as well, so you can see where the atoms are coming from, because I think it helps a little bit. Okay, so let's have a look at reaction with alcohol. Now these produce esters, so there's our acid chloride. We're going to react it with an alcohol, and we form our ester. Okay, so it's acid chloride plus alcohol will form ester plus HCl. So it's very similar to an esterification reaction. So remember, it is a derivative of carboxylic acid, except instead of producing water, we're producing HCl. So it's a lot more dangerous. And the final one is reaction with primary amines. Now this produces N-substituted amides. Well, it's a bit of a mouthful. Let's look at see what this is. So you can see here we've got ethanol chloride again. We're using the same acid chloride, and we're going to react that with a primary amine, as you can see there, and that's going to form our N-substituted amide. Now all that means is that normally with an amide, as you've seen before, you'd have NH2 there, but one of the hydrogens has been substituted for a alkyl group, as you can see here. Now the alkyl group in this case is methyl, because we started with methylamine, as you can see there. So because this is substituted, we say it's N, and where the word substituted is, we write down what group is substituted for the hydrogen. So that's methyl in this case, and then you just name the rest of it ethanamide. So you've got 2 carbons there, so it's ethanamide. Okay, again, same products are produced there. Okay, so we've looked at them reactions with acid chloride. Very vigorous reactions. We've got a carbon that's literally been stripped of its electrons by 2 electronegative elements from the oxygen and chlorine. But there is another type of reaction where we're using acid anhydrides instead. So very similar reaction, and what you need to know is the reactions, again, reacting with water, ammonia, alcohol and primary amines, but this time we're going to react it with an anhydride. And so we'd seen anhydrides just a little bit before, and we'd seen one of the reaction examples. So anhydrides, just to go through what an anhydride is first, anhydrides are made from 2 carboxylic acids that are the same. Okay, these are the only ones that you need to know for AQA. So acid anhydrides are named by naming the known, named by knowing the carboxylic acid, by naming the known carboxylic acid it's made from, and removing acid at the end and adding anhydride to the end. Okay, so we'll remove the acid bit and put anhydride. So here's an example here. So there's our anhydride, or acid anhydride. So what we're looking for is the type of carboxylic acid is. Now you can see we've got 2 carbons here, and we have got 2 there. Now they're always going to be symmetrical and identical, so we only look at one of them and name it from there. So this one's going to be ethanoic anhydride, as you can see there, because this is the 2 carbons here. So it's not butanoic anhydride, and that may sound a little bit strange because you think, well, hang on, you've got 4 carbons there. Because they are the same, we just name one of them and we just say ethanoic anhydride. Okay, so as long as you know that, that's the main thing. Okay, so again, let's look at the reactions with water, ammonia, alcohol and primary amines. Now, the reactions are very, very similar to acid chlorides. There's nothing new here. It looks as though there's a lot of information here, but it's just very similar. The only difference is the products are slightly different. Okay, we're still producing or similar type reactions, but instead of producing HCl, we actually produce a carboxylic acid instead. And so these are a lot safer to use, but they are less vigorous. They're nowhere near as reactive as acid chloride, so that could pose a problem because they're a little bit slower if you are in the business of making some of these products. So let's have a look at the first one. We're going to take an anhydride and react it with water. Now this produces carboxylic acids. So there's our ethanoic anhydride. We're going to react it with water, and that's going to form ethanoic acid, and also we're going to produce another molecule of ethanoic acid in this case as well. So we're going to produce 2 of them. But again, I've color-coded it so you can see, where the molecules are, where they're coming from. Okay. So the reaction with ammonia produces amides. So here's your ethanoic anhydride again, and we're going to react it with ammonia. So you can see it's very similar to acid chlorides. So react it with ammonia, and we form a amide, so this is ethanamide, plus carboxylic acid. So remember what I said, it's exactly the same as acid chlorides, except instead of producing HCl, we're going to produce a carboxylic acid instead. Okay, so again, not too bad. Here's the next one. So this is reaction with alcohol produces esters. So here's our acid anhydride, and we're going to react it with an alcohol. And just like with acid chlorides, we produce an ester. There it is. And we produce a carboxylic acid. And then finally, here's the other one, which is reaction with primary amines produces N-substituted amides. So there's your ethanoic anhydride reacting with your primary amine. This is going to form, obviously, your N-substituted amide, exactly the same, plus carboxylic acid. Okay? So you can see there's a lot of symmetry with acid chlorides and acid anhydrides. So the reactions are the same. It's just obviously with acid anhydrides, you produce a carboxylic acid. With acid chlorides, you produce HCl instead. Okay, so what we're going to do is we're going to look at some reactions regarding this, and this is going to be a nucleophilic addition-elimination reactions. So remember what we said about acid chlorides having that strong delta positive on that carbon, which is really susceptible to attack from nucleophiles. So what we need to understand is obviously the reactions that you've just seen, but we also need to know the mechanism associated with that. And so this is what we're going to be looking at here. So remember what we said was we've got a really strong delta positive carbon there because you've got an oxygen and a chlorine that's stripping the electrons away from that carbon or pulling them away, and because they're really electronegative. So you're going to have, you don't just have one electronegative element, you've got two there. So what we're going to do is look at a mechanism for ethanol reacting with propanoyl chloride, okay, in this example, but it can be any reaction or any nucleophile there, such as you might, obviously we're going to use alcohol here, but it could be water, it could be an amine, or it could be ammonia. It could be any of the ones that you've seen, but the mechanism is the same. So here's our acid chloride, and you can see that we've got methanol as our alcohol here. We've got our symbols on here, delta negatives and delta positives, and lone pairs. So what's going to happen here is the lone pair on the methanol and the alcohol, this is a nucleophile, and so this is going to attack the delta positive carbon on the acid chloride. Okay, so with it being a nucleophile, it's nucleus loving, so it's going to, it itself has a lone pair of electrons, it's going to attack that delta positive carbon. So then a pair of electrons from the double bond is then transferred to the oxygen, so that breaks. Okay, and so then what we're going to do is form this intermediate. So this is the addition bit. So we say nucleophilic, as you can see there, addition, elimination. So the addition bit is this. We've basically bolted on the alcohol group, the whole lot, and that's stuck onto the end of this group here. But now we have two charges. We have a negative and we have a positive. So we've done the addition bit there. So that's the whole thing that's added on. Clearly that's not very stable because you've got some charges on there. Okay, so what's going to happen is the electrons from the oxygen there are going to reform the double bond again. So you've only just broken it, but it's going to reform it back again. Okay, and so then what's going to happen is, because then the carbon would then have 5 bonds, one of the bonds is going to break, and that's going to be the chlorine. So that CCl bond is broken, and so therefore, obviously, you form your, you're not quite there with your product, but you're forming another intermediate. Okay, so we've got a lot of arrows going here. There's a lot going on in this mechanism. So there's our intermediate. That's what we've just formed there. We've still got that positive charge on the oxygen. However, we have a chloride ion that's floating around. As well. That's obviously just been removed from this molecule. And so what happens is the lone pair on that chlorine goes for the hydrogen on the OH group. Okay, because we need to neutralize this positive charge. So it goes for that, and then the electrons in that bond then go into the oxygen to neutralize that positive charge. Okay, so then we then finally form our product, which is that, and there's our ester. So the mechanism there, it's probably one of the most complicated mechanisms you're going to see at A level. There's a lot going on there. You need to remember that mechanism. The obviously the reagents that we're using here was an alcohol, but that can be applied, like I say, to any of the other three, which is water, ammonia, and primary amine. So you know the mechanism is the same, so don't worry too much about that. Okay, so just be aware of that. Loads of marks on offer there. Okay, so the mechanism, like I said, applies to the rest of them, as I just said there, so I've jumped ahead again. Okay, so what we're now going to do is look at another type of reaction. So this is using, and we've seen it already, but using an aromatic compound here, and we're going to make aspirin. Okay, so again, you might have done this in school or college. You might have made aspirin. Again, it's a pretty straightforward reaction. It's a nice reaction. You get a nice white powder that's produced from aspirin. So aspirin is an ester. That's all it is. It's made by reacting ethanoic anhydride or ethyl chloride and salicylic acid. And we've seen some of the salicylic acid already, but here's our ethanoic anhydride. Well, we hadn't seen salicylic acid, but we've seen an aromatic compound. So ethanoic anhydride, and here's your salicylic acid here. Okay, so again, I've color coded where things are going to go. So we've got the blue, the red, and a blue from it over here as well. So that's salicylic acid. And so that's going to produce this, which is aspirin. Okay, and again, I've color coded it so you can see the hydrogen from the OH drops off, and the red bit here from your anhydride adds on to the end here. So this is, obviously this is your ester here. This bit is your ester bit, this bit here. And then obviously we're going to form ethanoic acid as well as a product, as a byproduct. So you can see here that ethanoic anhydride is used instead of ethyl chloride in industry. Can you think of the reasons why? So remember what we said about acid chlorides and acid anhydrides before? Well, it's safer, it's less corrosive. Acid chlorides are really, really nasty, very corrosive chemicals. You don't want to get them on your hands. And the other one as well is that actually we're not producing HCl gas. So if we used an acyl chloride instead of ethanoic anhydride, then we'd get HCl produced, and that's not very good to produce. It's a lot cheaper as well, so anhydrides are cheaper to use than acid chlorides, and also it's safer. It doesn't react vigorously with water. That's the key thing. Acid chlorides do. You've got to really handle acid chlorides with a lot of care. But with your anhydrides here, they're not as dangerous. Okay. So you need to know that reaction as well. So you can see there's a lot of different reactions here. There really is, a lot of ways in which you can use a carboxylic acid or its derivative to form loads of different products, such as obviously aspirin, and we looked at how you make soap as well, and biodiesel and esters, and all these different things. There's loads of different things that we're making here, so it's quite an interesting topic. Okay, so we're going to look at the last few slides now. So these last ones are really going to look at practical technique, okay? Because all these things here that you see in organic chemistry is about making a product, such as aspirin, such as biodiesel, such as soap, and things like this. But what we need to do is make sure that we've got a pure product, okay? And there's ways in which we can make it, and ways in which we can test to make sure it is pure. So the first way, which we've come across already, is reflux. Now, reflux is a technique if you want to heat volatile liquids. Remember, that's what I said before. So reflux allows us to heat these reactants really strongly, but we can contain all of the reactants within the conical flask. We can contain it in there, and we're not losing any to the environment. So because they actually condense against the Liebig condenser. So you can see here that when we heat our substance here, it starts to boil, it evaporates up here, it hits the condenser, and it drops back down the condenser and into the flask again. So we have water coming in, and we have water going out at the top here. So we've got this outer layer here that's surrounded by cooling water. So that allows our substance to condense against the side of the Liebig condenser and then back down. It allows us to heat things without losing our product. Now you'll notice that actually we're heating this in a water bath, so we're not heating it directly. This is because normally for the chemicals we're using under reflux, they are volatile, as we said, and they are flammable as well. So if we put a naked flame right near a flammable liquid in that flask, and I have seen it as well, where sometimes if this seal hasn't been sealed properly here, then you might get vapors of flammable gas coming out. And if this flame licks up and starts catches one of these vapors coming off, you can actually get a reflux condenser that's on fire. So you've got to be really careful with that. Okay, another type is distillation. So distillation is really used when we want to separate substances with different boiling points. And again, you might have seen this. Already in the lab. So what we're doing with distillation is we're gently heating the mixture, and that will result in compounds separating out in order of boiling point. So we heat it in here. Again, we're using an isomantle here or a water bath, So we're using something, not using a direct flame for the same reasons we mentioned before. So knowing the boiling points of the chemical you want to separate will allow you to decide how you're going to separate your compound. Okay, so if we know the boiling points of these, we can heat it to that temperature. So it works it works in a simple way, depending on what you want to pick up. But if your compound has a lower boiling point than your starting mixture, then you heat to the temperature of the boiling point of the compound you want to separate, and you collect that in a separate vessel on the side there. So in other words, we heat this up, and let's say one of the components of this boils at, say, 70 degrees. That will then evaporate up into this tube, and then it will condense against the column here. Because it's tilted this way, the liquid will run down and into this container here, leaving the liquid with a higher boiling point in here, which actually brings us on nicely to our next point. So if you've got a higher boiling point in there, you heat the mixture to the boiling point of the compound you want to separate, and basically your higher boiling point compound will remain in this flask here, and the one that you don't want will in here. So you're just doing it in exactly the same way. It's just dependent on what you want to collect. So distillation is really useful when we want to extract a chemical before it reacts any further. So a classic example is alcohols forming aldehydes to carboxylic acids. Now, when we use an oxidizing agent in there, for example, dichromate, potassium dichromate is used to oxidize alcohols. So a primary alcohol will oxidize to an aldehyde, but then it will continue oxidizing to a carboxylic acid. Now, if you just want the aldehyde, you have to use a distillation kit. You have to separate the aldehyde first, get it out of that reaction mixture before it reacts any further and produces a carboxylic acid. So you need to use distillation to separate substances where you want to take it out of the reaction mixture before it reacts any further. Okay? So we're going to look at redistillation and separation. So this is basically, okay, so we've made our product, so now we need to purify our product. So redistillation is used when we purify our volatile substances. So we've made it in reflux, let's say, and we're going to redistill it, okay? So it can be purified further again by using separation, but we'll look at that in a moment. So what we need to do is separate the useful organic product that we've just made, okay, in our distillation kit, let's say, from the impurities, and distillation can help us here. So it allows us to separate chemicals via boiling points. Remember, we've just seen that before. So we can collect the different substances by monitoring the temperature that they boil at, and we're collecting the different liquids as they come out of the condenser. So you can see here that we say, right, let's say if we've got our substance here and we know its boiling point, we can heat it up and collect it in here. Okay, so we can collect it in our flask, depending on what we're after. Okay, so basically we're just distilling it again to try and get out as much of that impurity as we possibly can. And so then what we can also do is we can actually separate it further. Distillation doesn't give us a very a guaranteed pure product, so we need to take another step to purify it, and we use it using separation. And so we use, and you might have seen this before, but separation is where you have a large flask like this with a big bulb on the top of it here. And basically a separation funnel can help by, if we add a drying agent into our substance, that can help to remove water. The drying agent will dissolve, you'll see on the next slide, the drying agent will dissolve in the liquid, and effectively we can remove water from that, but we can filter that through, run it through, and separate our compounds. But let's have a look and see how that works. So, like I say, your separation techniques are used to remove impurities that are dissolved in water. So let's have a look, bring that diagram back again. So all the products from distillation are put into the separating funnel. So this is this here, okay? And we add water to dissolve the soluble impurities, and we create an aqueous solution. So you can see here, we've got our aqueous solution here. So we add water to it. That's our original compound. We're going to add water, and that'll remove any soluble impurities that may be in there, will be dissolved in this layer here. And then what we can do, you can see there, so we've got two layers. So we've got our impure product at the top, and then we've got our aqueous layer containing any soluble impurities in there. We've got them in the bottom layer, okay? So what we want to do is run that off, and you've got to remember to remove the stopper. There's the stopper there. we've got to remove the stopper when we're doing this, and you might have done this yourself, I'm not sure, but if you've tried to run a liquid off with the stopper in, you effectively create a vacuum in the top here, and that stops the liquid from running out. So you have to remove the stopper to then drain the liquid out. Very, very important. Okay, so purification. So what we're going to do is take the impure product, which is this bit, this layer here, from the separating funnel, and we're going to add that to a round bottom flask. Okay, so we've taken all our soluble impurities have now been drained off. We may still have insoluble impurities in here. So for example, we may still have water in here. So we've got to remove the water from that substance. So anhydrous calcium chloride, so CaCl2, that can be added to our impure organic product here. And we can give it a shake. So we invert the flask and we leave it. And what will happen is our anhydrous substance will remove any water or aqueous substances that may be floating around in this, and it tries to give us a purer product. So, and then we filter, obviously once we've done that, we filter the solid drying agent to remove it. So we put it through a filtration technique to remove that. And in fact, that's what we're going to look at now. So we've got our solid floating around in our organic substance, so we need to remove that solid, and we separate solids from liquids by using a vacuum filtration. So you can see here that a vacuum is used to help separate the liquid and solid components thoroughly. So you pour your organic liquid in there with your solid that's in there, your anhydrous calcium chloride. We put on a vacuum. Normally that'll be some contraption attached to a tap. Normally, that creates a vacuum. It pulls your liquid. It pulls your liquid through on the bottom here. This is the bit that you want, and your solid at the top. You can effectively dispose of that or get rid of it. So this is the bit that you want to keep here. So you can use this type of filtration. So very simply, we put a bit of filter paper, we just wet it a little bit just to create a seal, put it on the top of the Buchner funnel, which is that bit there. We pour the reaction mixture into that with the vacuum line on, and effectively we have a reduced pressure. So this pulls the liquid through, and the solid will be left in that Buchner funnel, as I've said. So again, that's very simple technique. So you might have seen that. You might have seen that as well. You might have used it, should I say. Now, depends what you want to collect. So, for example, if you want to get the liquid, then you've got your liquid in there. But let's assume, let's tip it on its head a bit. Now, let's assume that actually we want to keep, we produced a product, and the product is a solid, and we've been purifying the solid. Then, a way in which you can purify a solid is by filtering it like this. Now, you'll have your solid sitting on the top in your Buchner funnel there. So that solid may not be purified. So if it is a solid that we're after, then we have to recrystallize that solid to purify it further. So let's look at how we can recrystallize. So this is if you've got a solid product and you want to purify your solid product. So you filter it through here, you get rid of some of it, but we need to recrystallize. So recrystallization is quite a refined technique. You've got to be very careful with recrystallization. So recrystallization is a method to purify solids, and the solvent chosen is really, really important. Okay, so it works in a very, very particular way. Like I say, you've got to refine your technique with this. So what we need to do is add just enough hot solvent to the impure solid to dissolve it. Okay, so we've got our solid from our Buchner funnel, we've got it in a beaker. Okay, and we're going to add a tiny amount of hot solvent to it, and so this means you'll have a really saturated solution. So we do not want to add more solvent than we have to, so it's just enough to dissolve it, okay, into our impure product. And then what we need to do is we allow, as that cools down, the solvent cools down, we get crystals start to form, hence recrystallization. And then your impurities will actually remain dissolved in that solution, as there's more of your product than there's impurities, or there should be, and so it takes a lot longer for them to crystallize out. So the crystals that you're forming is your product, that's what you want, and your impurities will remain dissolved in solution. And so then once we've got our crystals, then we have to filter to get our solid purified crystals. We have to get them, and then we wash that with very cold solvent to dry them off. So the reason why the solvent is so important in this case is because you want your impure solid to dissolve fully in the hot solvent, but it's got to be virtually insoluble when we wash it with the cold solvent. So if not, then your substance will dissolve in the hot solvent, then you can't actually filter it out. So the solvent is really important. The solvent could just be water, it doesn't have to be anything fancy, but it has to meet that criteria, otherwise you can't recrystallize it. Okay, so now we've purified our solid, we need to actually determine how pure it actually is. Now, the purity of whatever you've produced depends on if it's a liquid or if it's a solid. But if it's a liquid, then we're looking at boiling points. If it's a solid, we're looking at melting points. So we're going to look at a liquid. So if we've produced a liquid and we want to work out if that liquid is pure, then we need to work out its boiling point. Okay, so measuring the boiling point of that liquid can help you to determine if there's any impurities in there. And we can basically bring this distillation kit back in. Now, this is if you're testing the purity of a liquid, then we do this method. Okay, so we determine the boiling point of the liquid by using the distillation kit that we've seen already. And then if we gently heat the sample, we can measure the temperature at which it distills using the thermometer. Okay, so we want to measure very carefully, when does that substance start to boil? When does it start to evaporate? And then what we're going to do is take that boiling point value and compare it against the data book value of the product. Obviously, we know the product that we're making, so we can compare that against the data book. Now, your sample will contain impurities if your boiling point is higher than what's recorded in the data book, but also it's about the range in which it boils. So in other words, if it boils in a really sharp, like at a very specific boiling point, then you've got a pure product. If it's kind of boiling over a range of different temperatures, then you've got some impurities in there. It's not a pure product. What we've got to be really careful though, okay, is that various organic compounds actually have the same boiling point. So it's not an exact science for this one. What you've then got to do is take that purified sample and run it through, say, like NMR machines, infrared machines, mass spectrometers, all these different types of analytical techniques, which you'll see towards the end of year 2, so it's the last topic, where you look at different methods of analytical techniques to actually, nail down exactly what you've produced. Okay, so let's say you've produced a solid now, and you want to work out if your solid is pure. Well, what we're doing is we're going to measure melting point instead, because obviously we've got a solid and we're going to see what its melting point is. Now, we use a special bit of kit, something like this, and this is used, it's a melting point apparatus, and basically it's used to measure the melting point of your solid substance. So we're going to do this in a really simple way, where we take our sample, our solid sample, and we put it in a capillary tube. So you might have seen a capillary tube. It's just a very thin glass tube that you have to seal the end of. You put it in a Bunsen flame and it melts the end of the tube. And then what you do is you tap your capillary tube against a solid product, like that. Okay, so you tap it, and then what happens is your solid will then get pushed into that tube. And then what we do is you then place it into this machine here. Okay, so you put your sample, your capillary tube in there, and then you look down this bit here. So you've got a viewfinder that you look down. And basically what happens, what the machine will do is it will gradually increase the temperature really slowly until the substance starts to melt. And what you're looking for here is a temperature range, okay, from when the solid just starts to melt. You'll see it just start to turn to a liquid, and then when it fully melts. So what you want to do is record down what that range is. And so then, essentially, the sharper that range, the less impurities you got. If the range is quite broad, then you got impurities, similar to what we did with the liquid. But again, we compare the value that we got against data book values, and we're looking for the same type of things we'd seen before. If it contains impurities, then we'll get a broad melting point. But also, if your substance does contain impurities, the melting point will be lower than what it says in the data book. That suggests that you do have some impurities in there. So you can see all of this is vitally important for organic chemistry, because obviously if we made a product, we need to know A, what we've produced, and B, is it pure? If it's got all salts in it, then that's no good, particularly in pharmaceuticals. You really can't afford to have impurities in that drug. You need to make sure you've got a pure product in there. Okay, and that's it. So that's the end of this video on carboxylic acids and derivatives. As you can see, there's a lot of information there, a lot of mechanisms, a lot of reactions. There is a full range, like say, of AQA revision videos like this on Allery Chemistry YouTube channel, as well as whiteboard tutorials as well, looking at general information about chemistry, and also some exam technique videos as well. They're all for free. All I ask is you hit the subscribe button. That would be absolutely fantastic. And also, again, these are available to purchase. Really good value for money. Just click on the link in the description box. Okay, that's it. Okay, bye-bye.